All right, so let's start off by going over learning objectives for work, power, and energy. So let's flip over to the page that is not numbered, but it should look right here where it says work, power, energy on the learning objectives. This one has quite a few. All right, there are 4 objectives for work. Let me just read through those really quick. Students able to make predictions about the changes in kinetic energy of an object based on considerations of the direction of the net force of the object as the object moves. All right, so basically, you're given a force onto an object, and you should tell me how is the kinetic energy going to change with a given force. Students able to use net force velocity vectors and velocity vectors to determine qualitatively whether the kinetic energy of an object would increase, decrease, or remain unchanged. Then, the student is able to use force and velocity vectors to determine qualitatively or quantitatively the net force exerted on an object, and qualitatively whether the kinetic energy of the object would increase, decrease, or remain unchanged. So essentially you're using forces and velocity vectors to tell me would the kinetic energy increase, would it decrease, or would it stay the same, and then you should be able to quantitatively calculate the net force. So given a free body diagram, what's the net force? And given a free body diagram, will the kinetic energy increase or decrease or stay the same? Does that make sense? Whoop. Got your best.
Here you go.
Just barely making it in. All right. The student is able to apply mathematical routines to determine the change in kinetic energy of an object given the forces on the object and the displacement of the object. All right. So this is all centering around work. Now the big thing with work, there are 2 things. Number 1, where did I put my marker? Right here. So work is the first one. And work is equal to the change in energy. Work is the change in energy. All right. Also, work equals force times distance. So work is the change in energy, and work is force times distance. A quick example of this would be you have Kelly Tobin sliding in to the home plate.
Wow, you're a twin, basically.
Right?
She's a resemblance mechanic.
Although you're technically going to be on the ground, so it'd be like you play like baseball or something like that.
I used to actually play baseball when I was like in elementary school.
All right, so yeah, whatever. I don't care. So, I'm kidding. That's a joke. All right. I want to know if when she reaches the base, she's at rest, right? And if initially she is traveling at 10 meters per second, right? And she has a mass of, say, 5 kilograms. All right? I want to know what, so first off, what is her change in energy?
Yeah.
What is the change in energy? All right? So first off, what type of energy does she start with? And how much energy does she have when she ends? You start with kinetic energy. What's the equation for kinetic energy?
1/2.
1/2 mv squared. Right? And how much energy do you have at the end here? 0, because you're at rest, right? So we have 1/2 mv squared minus 0. Because it's final minus initial. Or, I guess it would be 0 minus that. So it should be 0 minus 1/2 mv squared. All right. So you get v is 10, so that's 10 squared is 100 times 1/2 m should be 1/2 times m is 2.5 times 100, so 250 joules. Negative 250 joules is the delta E. Okay, see how I did that? Does that make sense how we got that? All right, so now the question is, if she was, we'll say, 13 meters, right? 13 meters away from home plate when she started sliding, what is the force of friction acting on her? If you're 13 meters away. Well, we know work is the change in energy, and work is force times distance.
So equal that to F times 2.
Now be careful though, because it is F parallel times distance. Now is friction parallel to the movement? Yeah. So then you can just use friction here. But if it wasn't, then you'd have to find the parallel component and then plug it into that. But in this case, it should be.
What do you have in for F zero?
That's the force of friction. That's what we're trying to find.
Oh.
So just to walk you through this, basically we say, all right, delta E is equal to work. Therefore, W now equals also to negative 250 joules. Right? And work is force parallel times distance. So this is going to be equal to force parallel times distance. So we get negative 250 equals, and force parallel in this case was going to be the force of friction, and the distance is going to be 13. So you get force of friction divided by 13, or sorry, 250 divided by 13 is your force of friction, which comes out to be what? Can you find the answer? 19? Negative 19.23 newtons is the force of friction. Does that make sense how we get that? Yeah.
Would applied force matter?
Would there be an applied force in this case?
I meant like if there was, but it's still.
Like if she had like
Something with like pushing on.
a rocket backpack?
Sure.
Yeah, okay, yeah. Would that matter? Yes. Yes, it would, because this is going to be your the net parallel force, essentially, right?
Okay.
So you got to think about like the resultant force after you combine everything is what's ultimately doing the work here. That's a great question. Yeah.
Both of those on our equation sheet?
These are both on your equation sheet. Everyone take your equation sheet. Right smack dab in the middle. Delta E equals work, which is equal to F parallel D, which is that's sine theta. Yep.
Found it. Found it.
All right, so that's work. Any questions on that? Again, I'm going to kind of go through the objectives, go through a brief example, and then I'll let you guys work on a couple practice problems on it together. Yeah.
Okay, I know why it's negative because like of the problem, but like how can it be actually negative in an actual situation?
The basic thing is that this represents your displacement,
Yeah.
and so we said positive 13 is from where you started,
Yeah.
where you ended up. So that means
Like-
positive is to the right.
Okay.
Which way is friction pointing?
Oh.
To the left.
Okay.
That makes
So
sense?
friction can be negative?
Friction absolutely can be negative. In fact, most times it is. All right, so that's work. So now on to conservation of energy, which has quite a few. That's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 learning objectives. All right? So let's just quickly run through these. We're not going to spend all day on this, but you should be able to calculate the total energy of a system. And then justify routines used in the calculation of component types of energy within the system whose sum is the total energy. So, you should be able to calculate total energy. You should be able to calculate the potential energy, the kinetic energy, and then the elastic spring potential energy. Does that make sense? The student is able to predict changes in the total energy of a system due to changes in position and speed of objects or frictional interactions within the system. This is a good example of your LOL diagrams. You guys remember those?
Yeah.
Taylor doesn't remember them. That's okay. I think this was right when you were joining the class. No? Okay, that's right. The student is able to make predictions about the changes in mechanical energy of the system. And so that's kind of exactly what we said before. It's like the same thing, isn't it? Okay. Parallel or anti-parallel to the direction of displacement of the center of mass. All right, here's one kind of what we did right here. The student is able to apply concepts of conservation of energy in the work energy theorem, determine qualitatively and or quantitatively that work done on a two-object system in linear motion will change the kinetic energy of the center of mass of the system, the potential energy of the system, and or the internal energy of the system. So again, just your LOL diagram. So like if somebody's trying to push a car that has the e-brake on up a hill, right? How are the forces going to change? How is the total energy going to change? How is the kinetic energy going to change? All based off that. All right? Everyone's giggling. Stop it. All right? The student is able to apply the concepts of oh, wait, I just said that. Okay. The student is able to set up a representation or model showing that a single object can only have kinetic energy and use information about that object to calculate its kinetic energy. So basically it's saying that if you have a cart on a ramp and the cart is not moving, what type of energy does just the cart have? That's the thing, is it doesn't. You need to have the cart earth system have potential. That's why on the O of our LOL diagrams we always included the earth, is because you needed both the cart and the earth involved in your system in order to have any potential energy. For example, if you're out in deep space, right, and there's nothing nearby, and you let go of a book, what's going to happen to the book? It's going to just float away. It's going to stay right there, right? And so that's the idea of that. Why you need the earth, right? Without the earth, nothing's going to fall, so it has no potential to do work. Does that kind of make sense? You need to have another body there in order to have a potential energy.
So what was that?
So if it's on a hill and it's not moving, not including the earth in your system, just focusing on the cart, you would have no energy at all. Now the cart earth system would then have potential energy. Does that kind of make sense? Okay. Student is able to translate between a representation of a single object, which can have only kinetic energy, and a system that includes the object, which may have both kinetic and potential energies. All right. The student is able to calculate the expected behavior of a system using the object model, i.e. by ignoring changes to the internal structure to analyze the situation. Then, when the model fails, the student can justify the use of conservation of energy principles to calculate the change in internal energy due to the changes of internal structure because the object is actually a system. I have no idea what it's saying.
Me either.
All right, we're back. Back to the objectives. We were just talking about how if you do not include the Earth in your system, then gravity is viewed as an external force, and therefore energy is not conserved. So that's why we always include the Earth in our system, because then gravity will be an internal force, and energy will be conserved. So that was learning objective. Well, that was back earlier. So that was learning objective 5B12, 5.B.1.2. We're saying that single object, which can only have kinetic energy, and a system that includes the object and something else that has both kinetic and potential energy. All right. Onto 5.B.3.1 says the student is able to describe, make qualitative and or quantitative predictions about everyday examples of systems with internal potential energy. This is like a book up in the air has internal potential energy because the book and the earth are both in the system. All right. The student is able to make quantitative calculations about the internal potential energy of a system from a description of a diagram of that system. So based off of the picture, you should be able to tell me how much potential energy is here. Or does the potential energy increase or decrease? The student is able to calculate changes in kinetic energy and potential energy of a system using information from representations of that system. So, like a roller coaster example, which is one we'll do here. The student is able to calculate, the student is able to design an experiment and analyze data to examine how a force exerted on an object or system does work on the object or system as it moves through a distance. So basically, you should be able to create a lab write-up that kind of outlines how would you use these equations here. All right? It's kind of leaning a bit. All right. Student is able to predict and calculate from graphical data the energy transfer or work done on an object or system from information about a force exerted on the object or system through a distance. So same thing as before, but now not only are you designing an experiment, now you're taking data from a similar experiment from there and analyzing it. All right. So those kind of go hand in hand. Like normally a lab write-up question, right, is how do you collect data and how do you analyze that data? Those are the two parts involved. And then 5.b.5.4, the student is able to make claims about the interaction between a system and its environment, in which the environment exerts a force on the system, thus doing work on the system and changing the energy of the system. I'm trying to think of like an example of this. This would be like something colliding with a wall, right? So like when a cart goes down a ramp and runs into a wall, it goes from having kinetic energy to not having kinetic energy, right? So where did that energy go? Well, it went into sound, into light, into thermal energy like that. And then the last one, students able to predict and calculate the energy transfer from an object or system from information about a force exerted on the object or system through a distance. And again, that's just being able to use work equals F parallel times distance. All right? That was a lot of objectives all at once. So that's kind of what we need, where we need to be at for that. Okay? So let's just really quick here open up our books to chapter 6. All right? So what I want to do is I want to skip over the multiple choice right now, and we're going to go to the first free response question there. All right, this is one you definitely have to be able to do. It says a box of mass M is released from rest at point A at the top of a long frictionless slide. Point A is at, oh, sorry, this is page 113. Page 113. Sorry about that. Yes.
Can you say this is like a problem that we need
I'm not going to say no. Anyway, so we have point is at height h above the level points B and C. Although the slide is frictionless, the horizontal surface from B to C is not. Therefore, the coefficient of kinetic friction between the box and the surface is mu k. And the horizontal distance from point B to C is x. Notice how many numbers are given here? None. Yeah. So find the speed of the box when its height above point B is 1/2 h. And I assume it means do that in terms of the given quantities. Find the final speed of the box when it reaches point B. All right? And then determine the value of mu k, so that way the box comes to rest at point C. Okay, think back to this example here. All right, you see how we're able to get force of friction? Now, how do we get mu from force of friction? Well, I hear it's a lot of fun. Right? So you can do that and then get it that way. So I'll let you guys work on this, and then maybe in like 10 minutes we should be able to finish this up.
I remember doing
All right, I know you guys would love more time to work on this, but we gotta wrap it up. So let's just really quickly here, let's go through this one. Okay. So with this guy, we have a big slope right here. So we go from A to B to C. All right. Now, going from A to some midpoint right? That's what it's asking. What is the velocity at the midpoint? You have to realize that we are going, I'm going to call this spot Z, right? So I'm going to say the total energy at A is equal to the total energy at Z. Again, I just labeled that point Z because I think it's a cool looking letter. Now the energy at A, we have your UG plus EK. I'm not even going to write US because there's nothing elastic going on here. I'm not going to write anything about rotation because there's no rotation going on here either. And so then at Z we have UG plus EK. Now, at A we know that there is no kinetic energy. So what we end up with is now mgh, which is at A, equals mg. Now what's my height at point Z? Half h, right? H over 2. All right? Plus 1/2 mv squared. So we got to solve for v, so this is just a bit of algebra. Right away you should notice that the m's cancel out. So that it says gh equals 1/2 gh plus 1/2 times v squared. So what I'm going to do, I'm just going to multiply both sides by 2, cancel out these 1/2s. So we get 2gh equals gh plus v squared. So now I subtract the gh over, I get gh, because 2 minus 1 is just 1, times v squared, so v equals square root gh. See how I did that? So really from this point on, it's just algebra. Alright, so that's that one. So now what about velocity at B? Alright, well now, if we're looking at here, total energy of A equals total energy of B too, right? Total energy of the whole system is conserved. And at point B, what do we know about the potential energy at B? That's also 0, right? So that goes away here. So now our equation becomes mgh, again that should be capital H, because that's the height at A, equals 1/2 mv squared. Alright, so now the v is what we're looking for. Again, the m's cancel out. And so we get 2gh equals v squared, so v is square root 2gh. Does that make sense? Alright, so the question then asks, what is the coefficient of friction in this friction-y part right here? Remember that's in black. Oh my god, there's so much friction. Well, the first thing you have to know is that if you go from potential energy to kinetic energy to at point C, rest, where there is no energy, you need to know that energy now is no longer conserved when you're going from B to C. Now it's no longer conserved because there's an external force acting on the system. And so, in order to find that force, we have to look at the work done by that force. So we say that work equals delta E. So let's look at the delta E from B to C. What type of energy do we have at point B? Kinetic, right. So we have EK here, 0 joules there because it's completely at rest and it's on the ground. So our delta E now becomes 0, or final minus initial, so 0 minus EK, right, is our delta E, and that's going to be equal to our work. All right. So, kind of moving along here, we then see that we have, well, let's go ahead and calculate delta E first. What do we want to do? Yeah, we'll do that first. So we get delta E is 1/2 m. And now what is V when you're at the bottom? We just solved it, right? What was V at the bottom? Square root of 2gh, right. So you get square root of 2gh squared. Right? Yeah.
Do we have to like substitute that in for this?
Technically, no. It
Like,
doesn't
can you
specify.
keep it as V squared?
You probably could leave it as v squared. Yeah, it doesn't specify. And so we now get delta E equals 1/2 m times 2 times g times h. All right, so as you can see, the 2 is also cancel out then. All right. So that's from here to there. So now the work done is going to be equal to force parallel. So we're going to say force parallel times distance. Right? That's the other part of the equation on your equation sheet. Now the force parallel is going to be friction in this case. Friction is acting as our parallel force that's taking away the energy of the system. So we now get delta E is equal to force of friction times distance. That distance was labeled as x, right? So we end up getting mgh, right, because the 2 canceled out, equals force of friction times x. All right? Now, force of friction is a lot of fun, so we get mgh equals mu Fn times x. And so now we end up with mu equals mgh over Fnx. Can we simplify this down any more? Yeah. What is the normal force when you're on a flat surface? Well, it's just equal to your weight. And when your weight is just mg. So we get mu equals mgh over mgx. Mg's cancel out, so we get mu is equal to h over x. Now, technically, the question didn't tell you to simplify it down that much, so I think if you left it as 1/2 mv squared divided by Fnx, that probably would have been fine too. Okay? Yes?
Wouldn't it be negative? Because it's like 0 minus, like final minus initial, so would you have mu equals negative h over x?
That is a good point. Yeah, that's a good point. The one thing is that the force of friction would also be negative to cancel that out because it's a negative. Yeah, sorry, that was a great point. I forgot that. I lost my negative. All right. The last two parts of here get a little bit weird. I do want to talk about them though really quick because it is a little bit interesting. In that now they say that this bottom frictiony part is still a length of x. So I'm going to erase all this. But now there is also a slope, an incline. Sorry about that. I just don't want to redraw my whole picture. All right. I know you guys probably have to go. We're already past 5:30. But here's our height y now. So now, when we look at our delta E, so we still have delta E is equal to work. And so we're going to still do the same thing, right? Still asking for mu, I believe, right? But now our delta E would go from EK to UG plus, or we'll just leave it at that. And so now our delta E would be UG minus EK. Does that make sense? Yeah.
Would you not have any EK at C either?
Yeah, because it still stops moving at C, and you're still stationary at C, but now you're up a height y. And so now you're going to do the same calculation where you set this equal to the force of friction times x. But now you're going to have mgh, and your h at this point is just y. So you're going to have mgy minus 1/2 mv squared equals ffx. All right? And this is where I do have to say that having the velocity plugged in here as square root of 2gh really makes things a lot simpler because the mg's line up a lot better. You can factor out some of that stuff. But I'm not going to go through all the algebra here just to save some time. But this is a general step. You now solve for mu at that point. And then let me just check what was the last bit on here. The last question was, if the slides were not frictionless, determine the work done by friction as the box moved from point A to point B. So the speed of the box as it reached point B, where half the speed is calculated as part B. So again, in order to do that now, the work done by friction, you would still have to find that change of energy. So it's saying that when you go from A to B, the change in energy would be UG delta E equals the EK at the bottom minus the UG at the top. So you do that, start out from there, solve for the work, solve for the force from there. Or just solve for the work at that point. Alright, that's all the time we got here. If you want to stick around for more questions, you're more than welcome to. Other than that, that's all we got here. 9 a.m. tomorrow is going to be our next review session. It's going to be in this room. There will be Panera and coffee.